Hey, thanks for joining me for this final factoring polynomials uh, lesson. We're going to talk about putting them all together. So if you have not watched the previous 5 recordings, then you're missing out. Go back and watch those because you won't know what I'm talking about here. But in this recording, we're going to look at some what I think are tricky examples. Problems that require more than one type of factoring to factor them completely. And I want to kind of walk you through the thought process. Now, the first thing, step number 1 always, and we said this before, step number 1, GCF. GCF, finding the greatest common factor, is going to really narrow down our our problem, make it simpler. We're just going to simplify it a lot. So we'll do that here. Notice that here's my thinking here. 6 is 6 times 1, and 18 is 6 times 3, and 12 is 6 times 2. Now, what if you didn't notice that? What if you had said 2 times 3 is 6, and 2 times 9 is 18, but notice 9 is not prime, so we have to say 3 times 3. And then 2 times 6 is 12, but of course notice the 6 is not prime either, so we have to say 2 times 3 again for 6. So 2 times 2 times 3. So we could have broken this down this way, but then we would notice that there's a 2 and a 3, 2 times 3, which is 6, in each number. So however we do it, we notice what they have in common. Notice that the first term, c squared, has 2 c's, c, d in the second, but then the third one only has d squared, so it doesn't have any c's. And of course the first one doesn't have any d's, so we can't factor out any of the variables. So we're going to factor out the 6 from each term, and then we're left with, and I'll do it a different color just so we can kind of visually see what's going on here, c squared plus 3cd plus 2d squared. Okay, now if I take out the greatest common factor and I'm left with a binomial or a trinomial that looks like it might be factorable, I have to keep on going. I can't stop. Now, step number two is looking for those patterns. And that relates to step 2, the recording called Factoring Polynomials Step 2, Patterns. And we look for the basic pattern we're looking for. If it's a trinomial, we're looking at the first term and the last term and asking, are they both perfect squares? So c squared is a perfect square, d squared is a perfect square, but the 2 is not a perfect square, and so this does not fit into our factor patterns as the square of a sum or a difference. So we're gonna skip that step, but it's always good to think about that step, especially if we have binomials. Remember the big, well, we'll see them. The big patterns are the binomial difference of squares and sum and difference of cubes. Okay, step number 3 is just to do the factoring. Now, this one's a little bit trickier because we've got c squared in the first term, d squared in the second term, cd in the middle term. So what does that mean for us? That means that the first terms of our binomials, if these can be factored, are just going to both be c, and the last terms are going to include a d, because c times c is c squared, d times d is d squared, and then we'll have a term that has a cd in it and another term that has a cd in it, and those will add up in the middle. So once we recognize that, then we can see that the only thing that we're worried about is that 2 and that 3. In other words, what are the factors of 2 that add up to 3? And of course 1 times 2 is 2, and 1 plus 2 is 3. So there it is, plus 1 and plus 2. And of course, don't have to write the 1d. So there's our factors, c plus d times c plus 2d, and then we'll bring down the 6. We factored out the greatest common factor. We don't want to like drop it or misplace it. We want to keep it with us at all times. And those are the end results. That is the final answer. Now, it's always a good idea to check your answer by just going ahead and multiply the binomials together. C plus d times c plus 2d. Does it equal c squared plus 3cd plus 2d squared? And then multiply that by 6 to see if indeed you get back to 6c squared plus 18cd plus 12d squared. But this is the answer. And I used, what was the second pattern? It was x squared plus bx plus c. That was the pattern that we were looking for. And then don't forget that if there was a coefficient on the first term, we would have done the 4 square method. And then finally, if there had been 4 terms, we would have used the grouping method. If there had been 4 terms, we would have used in our polynomial. It's a trinomial, so there wasn't. But if it had been a 4-term polynomial, we would have gotten to the grouping method pretty quickly. Okay, so those are the 5 steps. We watched those 5 recordings already. That's the process of thought that we're going to go through as we go through these. We're just going to, number 1, look for the GCF, and then we're just going to say, well, does it fit into a pattern? Is it an easy trinomial? Is it a hard trinomial? Is it a 4-term polynomial? And use the appropriate method as we come to them. Okay, so I'm not going to write that down anymore. Let's go through the steps. Step number 1, common factor. Notice that they're all negative, and they all have a bunch of n's, not just one n, but n squared, right? N to the 4th power, n squared, n to the 3rd power. The smallest number of n's is 2 n squared. So we're going to take out a negative n squared, and we're left with n squared plus 3 plus 2n. Now, that's tricky enough, factoring out a negative n squared. But then what makes this one also tricky is that the trinomial that's left isn't really in a standard form. It's not a descending order, and so we want to change it into descending order, and we want to be careful that we don't lose our common factor, our GCF. So I'm going to write that down, negative n squared, and then I'm going to write n squared plus 2n plus 3. Okay, so I just changed the order, and I'm allowed to do that with a polynomial. I can change the order if I want to. If I had 4 terms and I wanted to do grouping and I didn't think the grouping was going to work with the given order, I can swap them around. And in this case, if it's a trinomial and it's not in descending order of the variables, then I can put it in descending order. N squared, n, and then the constant. Okay, now this looks like an easy trinomial, n squared plus 2n plus 3. The factors of 3 that add up to 2. Well, let's see. 1 times 3 is 3, and 1 plus 3 is 4. And negative 1 times negative 3 is 3, and 1 plus negative 1 plus negative 3 is negative 4. Now, wait a second. There are no factors of 3 that add up to 2, so therefore, this cannot be factored. This is a trinomial in standard form with the variable squared plus something times the variable plus something else. It can't be factored. They tried to trick us into thinking it was going to be the factors of 2 that add up to 3, which would work, but that n there is messing that up. So this is as far as we can go. This is a case where we have a trinomial that cannot be factored, and that's okay. We took out the greatest common factor, and that was all we could do. Well, let's move on to the next one. Now this one should be fairly easy to get the GCF out of here, but yeah, those are big numbers. So I'm going to try breaking them down in a row here. Well, I'll do it off to the side here. So I'm going to take 80, that's, oh my goodness, it's 8 times 10, right, which is 2 times 4 and 2 times 5, and then 4 is 2 times 2. So there's 1, 2, 3, 4 2s, so it's 2 to the 4th power times 5. Okay. And then let's do the 120. We don't need to worry about the negative. So 120, we know that's not going to be a common factor. Well, that's 12 times 10, and that's 4 times 3, and that's 2 times 5, and that's 2 times 2. So that's 3 2s, 2, oh, I said 3, but I meant to write 2 cubed, times 3 times 5. Okay, so there we go. And I may decide at the end that it's not to my advantage to write these in exponent form, but for now that's what I'm doing. So I know 45 is 5 times something. 5 times, what is that? 5 times, well, 5 times 9. And then 9 is 3 times 3. So this is 3 squared times 5. Alrighty. So now that I've got these factored, I factored them completely down into their prime factors, and then I notice that 80 has a bunch of 2's and a 5. 120 has a bunch of 2's also, and a 3 and a 5. And 45 has several 3's and a 5. So the only common factor here is 5. So that's kind of disappointing. I was hoping I would have more, but that's what I've got. So I'm going to take out the 5's, and then I'm going to just rewrite this with the 5 factored out. Now, if I want to, if I'm more comfortable with this, I can change the order. Notice that the p squared term is positive, so there's no problem putting it in the front. So if I take out the 5, I'm left with 3 squared, which is 9, 9p squared. And then the middle term would be the negative 120p with the 5 factored out, which is, let's see, 3 times 2 is 6, then 12, then 24. So negative 24p. And then plus the 80 divided by 5, which is 2, 4, 8, 16. 16, right? Okay, so there it is. I took out the 5, and I rearranged the order just so I'm a little bit more comfortable. Again, if it had been negative 45p squared, I probably wouldn't have wanted to do that, but it's always nice to have that first term be positive. But now we can look at this problem, 9p squared minus 24p plus 16, and we can kind of address it as a trinomial. It's maybe not as simple as we would like it to be, but it's simpler. Now, let's go ahead. I'm not sure if this is going to work, but let's try our patterns just in case. So 9p squared, that is really 3p squared, 3p times 3p, right? It's 3 times 3 is 9, and p times p is p squared. And 16 is 4 squared. Okay, so now I'm getting a little bit excited because it seems like this might fit one of my patterns. If this middle term is 3p times 4 times 2, then it's going to fit into that binomial square pattern. So 2 times 3 is 6, times 4 is 24. Oh, it does work. 24p, so the middle term is 2 times the square root of the first times the square root of the second, the last. So this is going to fit into that formula where we have a squared minus 2ab plus b squared, which is equal to a minus b squared. So if I can see that, then this is going to save me a whole lot of trouble. Let's go ahead and write the answer. We're done. 5 times 3p minus 4 squared, which means 5 times 3p minus 4 times 3p minus 4. So that's two binomials. Don't be confused by that. Now 3p minus 4 squared is 3p minus 4 times 3p minus 4, like I said. And 3p minus 4 can't be factored any further. We know it can't be factored any further because we just have p to the first power. We took out the greatest common factor, and once we get p to the first power, there's no, in our polynomial, it's a binomial with p to the first power, or the variable to the first power. It means that we're done. There's nothing else we can do. So this is it. Now, remember back in step 2, and I said this pattern wasn't very important. Well, now you're saying, yeah, I think it was very important. But notice that we could have factored this using our step 4 method. We could have done 9 times 16, what are the factors of whatever that is, that add up to negative 24, and we could have done the 4 square method, and it would have worked. It would have worked, and we would have gotten 3p minus 4 times 3p minus 4. So it would have worked, but you're right, this was a lot easier if we could recognize the pattern. Okay. Let's do another one, and this one's a binomial, which should make us very suspicious. But before we get into that whole binomial thing, we have to take out the GCF, as always. And notice that we have 8, which is 2 times 2 times 2, and 18, which is 2 times 9, 2 times 3 times 3. So there's a common factor of 2. They both have a p in them. The first one has a p cubed, the second one has p, first power. They both have a q in them. And it's kind of reversed, right? The first one has a q to the first power, the second one has a q to the third power. So we can kind of visually see that there is a common factor of 2p cubed. If I take that out, then I'm left with 8 divided by 2 is 4, p cubed divided by p is p squared, q divided by q is 1, minus 18 divided by 2 is 9, p divided by p is 1, and q cubed divided by q is q squared. Once I take out the GCF, the greatest common factor, which I don't want to lose, this is part of the problem, this is part of that expression. But once I take that out, we can see that this is a difference of squares. This is 2p squared minus 3q squared, and so that will be really easy to do. So this is going to become 2pq, so our greatest common factor, times 2p minus 3q times 2p plus 3q. I think I did it backwards from what I showed you before, but that doesn't matter. Order doesn't matter. So 2p plus 3q and 2p minus 3q is the same thing. That is our difference of squares formula. That one's the really, really important one. I said is it shows up all the time, and it's the only way to factor. There's no other way. So I'm glad we were able to identify that. There's two ways to do this one, and this one's a tricky one. Notice that this is really an expression that just hasn't, frankly, it hasn't been simplified. We need to simplify it. We should just distribute here and distribute here, and we would get n cubed minus n plus n squared minus n. And then when we combine like terms and put things in the right order, we get n cubed plus n squared minus 2n. And then we can factor out a greatest common factor, which is n, and we're left with n squared plus n minus 2. And then we can do our thing with the factoring, what are the factors of -2 that add up to 1? And I think you can see that that's +2 and -1, so n plus 2, n minus 1, and then the n out there, and that is the answer. And for this problem, that probably was the best way to go. We simplify the expression, do all the multiplication, so that we can see all our terms. There was 4 terms, but we could combine a couple of them. So we ended up with a trinomial, and then we just went through the steps, factor out the greatest common factor, and then do the easy factoring, and it was pretty simple. I want to show you that there's a second way we could have done this one. We could have thought of this kind of like it's like a half-done grouping problem, right? It's like we factored out an n, but the two groups were still not the same, but they're close, right? So we could say, well, what else? N minus 1 can't be, is as simple as it can get, but n squared minus 1, that should make us think of something, right? That's n plus 1 times n minus 1. Now, if we just bring down the rest of the problem here, n plus n times n minus 1. Now, what do these two binomials have here? Well, this is a binomial, right? This is two terms. The first term is n times n plus 1 times n minus 1, and the second term is n times n minus 1. So there's an n and an n minus 1 in both cases. So if I take that out, n times n minus 1, what am I left with inside the brackets? I took out the n and the n minus 1, the n and the n minus 1. So I'm left with the n plus 1 there, plus, well, I took out everything here, so if I divide out everything, I'm left with just plus 1. Well, what is n plus 1 plus 1? Well, n plus 1 plus 1 is n plus 2. All right, and so now we see that being really competent and confident with our patterns and the different methods, the grouping method, the difference of squares pattern, we can come up with the answer in a different way than just brute force multiplying, distributing, getting it into a trinomial, and then trying to figure out how to factor it. So either way works. I thought that second method was a little bit more fun than the first method, but you can do either one. All right, let's get back to brass tacks here. Let's do this one. Notice again we have a trinomial and it's out of order. It's going in ascending order. So from a to the first power to a to the third power to a to the fifth power, instead of our normal descending order where the powers decrease. Okay, so we might want to change that, and we can because the one that should be the first term is positive. So, but while I'm thinking about doing that, I'm also going to think about what's the common factor here. And notice that we have a cubed, a to the fifth, but the coefficients are 81, 18, and 1. So the common coefficient factor is going to be 1, so 1a. And then if I want to go ahead and swap these around, I'm going to write a to the fourth power, that's the a to the fifth divided by a, plus 18a squared, that's a to the third divided by a, plus 81, that's 81a divided by a, and there we go. Now, this is tricky because we have a to the fourth, and we don't really have any method of factoring when we have a to the fourth power, right? We've only dealt with squared. So here's a trick that we can use, and I'm gonna do this trick down here. I'm gonna say, let's say that a squared is equal to x. So then a to the fourth power would be x squared. So we can rewrite this problem as x squared plus 18x plus 81. And you're allowed to do that, and then we can kind of evaluate it from there, and maybe we can recognize that this is a perfect square. Maybe we'll say, what are the factors of 81 that add up to 18? And eventually we'll find it's 9 times 9, so this is x plus 9 times x plus 9, which is x plus 9 squared. But then remember, x is our code for a squared, so it's really a squared plus 9 squared, and then of course don't forget the common factor of a, and so there's my answer. Now, I don't think we had to go that route. I think we could have recognized that this is a times the quantity. A to the fourth power is just a squared, and then 81 is 9 squared, and then 18 is 2 times 9, and then a squared. So then this fits into our pattern of the binomial squared. So we've got a something squared plus, and then the last term is something else squared, and then the middle term is the two square roots multiplied together times 2, and that fits into our binomial square thing. And so we could see that this is really going to be a squared plus 9 squared, and then of course don't forget the common factor that we took out at the beginning, which is a, and there it is. So notice that there's more than one way to think about these problems, and that's what makes them tricky, because you have to think about all the different ways of factoring and see which one kind of makes sense to you for this problem. And sometimes one way of looking at it will work better, and sometimes another way will work better. Okay, let's do m minus m to the 8th minus n to the 8th. I wanted to show you this problem. It's very similar to the last one because it's a binomial. So the only thing that can be going on here is a difference of squares or difference of cubes, right? That's the only pattern. We don't have any other methods. Well, these aren't cubes, right? The 8th power is not a cube. We can't even divide it by 3 evenly. But we need to recognize that m to the 8th power is the same as m to the 4th power squared. Because it's kind of like the last problem where we recognize that if we take our power to a power, we can turn it into a square there. And once we recognize that it's m to the 4th squared minus n to the 4th squared, we can factor m to the 4th plus n to the 4th times m to the 4th minus n to the 4th. And there we are. We applied our difference of squares formula, and we factored it. But are we finished? And this is always the question. Remember I said one of the previous problems that if we have p to the first power, or x to the first power, m to the first power, if we have something to the first power, then we're done. We're done. We can't do any more. But if we don't, and we don't here, we have m to the 4th power, n to the 4th power. If we don't, then we need to ask ourselves, can we keep on going? Well, m to the 4th plus n to the 4th, those are not a sum of cubes. Again, it's not the cube, it's not m to the 3rd power, n to the 3rd power. So we don't have any formula for factoring m to the fourth plus n to the fourth. But m to the fourth minus n to the fourth might be a difference of squares if we recognize that m to the fourth is really m squared squared, and n to the fourth is really n squared squared as well. And if we can recognize that, then we can factor that one. So that becomes m squared plus n squared times m squared minus n squared. And of course, we can't forget the original m to the fourth plus n to the fourth factor that we couldn't break down further. That's still part of our answer. So now we've got this broken down into three binomials. M to the fourth plus n to the fourth, m squared plus n squared, and then m squared minus n squared. Oh, wait a second. M squared minus n squared, that's a straight up factor pattern. That's m plus n times m minus n. We've been doing that all problem long. So we can't do a square plus a square. We can't factor that. But we can factor a square minus a square. That's what the difference of squares factor pattern says. So that means that the first two binomials here with the fourth powers and the squareds and the addition cannot be factored any further, so we're stuck with those. But that m squared minus n squared becomes m plus n times m minus n. And so this is the complete factorization of this problem, even though to begin with we weren't sure we were going to be able to do it one time, and we ended up being able to factor 3 times. Okay. Now, if you haven't tried this yourself yet on these problems, see what you can do with this one. Notice that we kind of have possibly, well, we've got x to the 6th power, and x to the 6th really is x cubed squared. So we have to be suspicious of this. We've got the 64, so let's take that 64 and just break it down. 64, let's see, I'm going to do that. I know it's even, so I'm going to just divide by 2. So 2 times 32, and that's even. 2 times 16, and that's even. I think you probably know that that's 4 times 4. And that's 2 times 2, and that's 2 times 2. So, how many 2's is that? 1, 2, 3, 4, 5, 6. So 64 is 2 to the 6th power. So we had x to the 6th power minus 2 to the 6th power. So then this must be 2 to the 3rd power squared. Okay, now I could have recognized that 64 is 8 times 8. It's a perfect square. And so I could say here that it's 2, instead of saying 2 cubed, I could just say that's just 8 squared. But either way you think about it, this is definitely a difference of squares, so let's do it. Let's factor it. So that's going to be x cubed minus 8, or let's say plus 8, and then x cubed minus 8. Okay, now remember we said 2 cubed is 8, so let's rewrite this as x cubed plus 2 cubed times x cubed minus 2 cubed. And once we recognize that, then you say, uh-oh, that's the sum and difference of cubes. Now, if you're in Algebra 1, probably not going to see this one. Maybe you will. I don't think so. But if you're in Algebra 2, this is one that might show up. So let's do this one. X cubed plus 2 cubed, that's going to be x plus 2 times x squared minus 2x plus 2 squared, which is 4. And then x cubed minus 2 cubed is x minus 2 times x squared plus 2x plus 2 squared, which is 4. And so there we have it. That's the most obscure, tricky problem you'll ever run into. Don't worry about it if you don't remember the difference in sum of cubes. If you hadn't seen those before, or those ones drive you crazy, they don't show up very often. Okay, well, there we have it. That is how you apply our steps to factoring polynomials to factoring really complicated polynomials that require more than one step. Thank you very much for watching and have a great day.